What time are we at? 8 o'clock. 1, 2, 3, 4, 5, 6, 7. Okay, let's get started. And as people come in, they come in. All right, so I've started grading the exams. I'm not all the way done. I plan to have them in the grade book all by tomorrow. And you're gonna have until Friday to get corrections to me. Again, get corrections written up and sent to me, and you'll be able to get up to half of the points back that you missed. So if you got a 0 on the exam, nobody who takes the exam in my class ever gets 0, by the way. But if you did get a 0 on the exam and then you did all your corrections, your 0 would turn into a 50. Okay, if you got a 60 on the exam, your 60, if you did all your corrections, would turn into an 80, 40 over 2. Okay, so big point boost. All right, so make sure to get those corrections. Once I have those graded in the grade book, send your write your corrections in a different color than you did the exam. So just you'll have your exam file through Canvas, whatever color you wrote. I grade in red, and so hopefully you wrote your exam in black. So do your corrections in blue, or do them in whatever color you didn't do the exam the first time around. Okay. So don't make any alterations, because I'll also have the exam, and it would be weird if you change something and then try to get extra points that way. So don't do that. Okay. All right. That's that. Questions? Don't forget you have homework. It's going to be over this stuff. That's due on Monday. Okay. So, all right, let's dive into my favorite integral. Find the integral of sine of natural log of x with respect to x. All right, so the integral of sine of natural log of x with respect to x. We're talking about integration by parts today and yesterday, and really for the rest of the semester, integration by parts is always going to be a viable option for us to use when we're taking an integral. Okay, so this, if you tried looking at this right away, my first guess to do this integral would be use a u substitution. Use u equals natural log of x, and then du is 1 over x. Du is 1 over x dx. But if you do that, that doesn't really get you anywhere, because then to handle this, you need to solve this for x. X is e to the u. And so dx is, well, it's x du, so it's e to the u du. And then when you plug all that in, you end up with, well, sine of u times e to the u du, and you're still in an integration by parts situation. Okay, so if you want to make that u substitution and deal with this integral instead, you can, but we're just going to use integration by parts right away. So ignore all of that. We don't really want to do that. Instead, I'm going to tell you right away that for this integral, we're going to use integration by parts. And I'm going to make u, well, the only option I have to make u is sine of natural log of x, right? I don't know how to integrate sine of natural log of x, so it has to be u. It's got to be something I'm differentiating. So I'm going to make u sine of natural log of x. And then I'm going to make dv dx. Okay. So if u is sine of natural log of u, let's test out our Calc 1 chain rule powers. What is du? What are we going to get? Well, I use the chain rule. I'm going to get the derivative of the outside. I'm going to get cosine. I leave the inside alone of natural log of x. And then I multiply by the derivative of the inside, right? So multiplied by the derivative of the inside is times 1 over x, the derivative of natural log of x. Okay. And then this is times a good old dx. Okay. We'll do the easier one. If dv is dx, then what is v? Austin, if v is dx, then what is v?
Would that just be x?
X. Perfect. Exactly right. So I plug this in to my integration by parts formula. This is the integral of, we're saying this is u and this is dv. Well, the integral of u dv is equal to, what's the first part of integration by parts? April. U times v, and then minus the integral of what? v d, you swap them, v du. No, you're fine. Okay, so let's plug this in. uv is x times the sine of natural log of x minus the integral of v du. Well, v times du, this x is going to cancel the 1 over x, right? And I'm going to get cosine of natural log of x dx. So looking at this is almost identical to the integral we just did. So I'm going to do integration by parts again. But now on cosine of natural log of x dx. You guys are gonna love this. This is like a murder mystery. When you find out who done it, oh, it's so wonderful. All right, so let's look at the integral of cosine of natural log of x dx. Well, I'm telling you guys that you need to use integration by parts again. Well, again, the only choice that I have to make u is cosine of natural log of x. Because I can't, I mean, that's the whole thing, is we're trying to find that integral. I don't know how to do that integral, so I can't make it dv because I would have to integrate it. Okay, so it has to be u. That means dv is going to be dx. So du, I'll let everybody rest on this one. Du is, well, chain rule again. I'm going to get negative sine of natural log of x over x dx. And dv, or dv is dx, so that means v is x, right? So let's plug that in up here. Oh, I love this integral so much. So we're going to get uv. This is, again, this is u, this is dv. So we're going to get uv is x cosine of natural log of x minus the integral of v du. Well, this minus here is going to turn this into a plus. And so I'm going to get plus the integral of, well, v du is sine of natural log of x dx. So let's review what we've done. We started off with the integral. We started off with this problem, the integral of sine of natural log of x dx. We used integration by parts once to get this. So we got x sine of natural log of x minus this integral. So minus this stuff then, right? Minus x cosine of the natural log of x. And when I distribute the negative, I'm going to get minus the integral of sine of natural log of x dx. Okay. But this is where we started, right? We started off with that integral. So what should I do to both sides of this? Yeah, this is, if I call this integral I really quick, I have I equals a bunch of stuff minus I, right? I mean, who cares? I mean, we do care because that's what we're trying to find. But for a second, we're going to pretend we don't care. If I had an equation that was I equals a bunch of stuff minus I, well, I would just add I to both sides, right? And I would get, oops, I would get 2i equals that stuff, right? Well, now I'm going to actually write the stuff in. 2i is equal to x sine of natural log of x plus, or sorry, minus x cosine natural log of x. Okay. And again, I'm calling I that integral that we were interested in. Okay. So that means I, which is the integral that we care about. So I, which is the integral of sine of natural log of x dx is, well, I can divide both sides by 2 now. This is 1/2 times x sine of natural log of x minus x cosine of natural log of x. And then don't forget the c. And that's my favorite integral, or really my favorite type of integral. There are several integrals where this process happens. Anytime you have sines and natural logs happening together like this, or cosines and natural logs, or sines and e, or cosine and e, you get something like this, and it's wonderful. So are there any questions on this one?
Yeah, can you explain the I part again?
Yeah. So all I'm saying here is, if I call this thing, this integral that we're interested in, if I call that I, well, I have an equation that's I equals x sine of natural log of x minus x cosine natural log of x minus, this is the same integral. So this is minus I. So I have an equation that's I equals stuff minus I. And so I just add I to both sides. And when I do that, I get this equation where, again, I is the thing that we're interested in. And so to solve for I, well, I divide both sides by 2. And yeah, April.
Can you go back a few lines to the previous slide?
Yeah.
Where did that extra x, the minus x percent ln of x come from? I think it was in the next slide. You had,
Where?
it was somewhere where you had the extra, it was like x cosine ln of x minus x percent ln of x plus the integral sine ln of x. Yeah.
Here?
Yeah, that.
Yeah. Okay. So the first time we did integration by parts, we got this, right? So then I need to do integration by parts again on that guy. So that's what this process was right here.
Okay.
And when you do that, you get x cosine natural log of x plus that integral that we started with, right? So that was me substituting what that integral is into what we had done so far. Yeah, good question. Any other questions? Okay, this one's definitely tougher to wrap your brain around. So don't worry if it seemed a little weird. It is a little weird. Okay. But that's why it's my favorite. All right, so that brings us to integration by parts for definite integrals. And it should come as no surprise that because definite integrals use indefinite integrals, integration by parts looks almost exactly the same as what we've been doing, right? So by the fundamental theorem of calculus, we know that the integral from a to b of f of x g prime of x dx is f of x g of x evaluated at b and a and take a difference minus the integral of g of x times f prime of x with respect to x. That's written out in f's and g's. If I'm going to use a's and b's, which sorry, u's and b's, which is much shorter, we can just write it as the integral from a to b of u dv is equal to u times v, evaluate at x equals a, x equals b, and then minus the integral from a to b of b du. So really all I'm saying here is if you want to do an definite integral, do the indefinite integral and then plug in. I mean, it's the fundamental theorem of calculus. I almost didn't even put this slide in here, but to be complete, I thought I should. So let's dive right in. Let's find the integral from 0 to 1 of tan inverse or arctan, arctangent whatever you want to call it, arctangent of theta with respect to theta. Okay. So again, this one might not seem like integration by parts, but it's definitely not a U substitution. There's no composition of functions going on here. So if you ever see an arc trig function, integration by parts is a pretty good bet. So remember Lyautey to help us decide what should U be and what should dV be. Well, U needs to be, there's an inverse trig function happening here. So U should be arctangent of theta. Also, it's the only choice for U because I can't make arctangent of theta dV because again, we don't know how to integrate it yet. Okay. So that makes dV d theta. Okay, so who remembers the derivative of arctangent of theta? 5 seconds. 5, 4, 3, 2, 1. The derivative of arctangent of theta is 1 over 1 plus theta. Ah, sorry, I took it from you. Yeah, 1 over 1 plus theta squared. So then we have a d theta here. Okay. If dV is d theta, then what is V?
Theta.
Theta, exactly right. So let's plug this in. We've got the integral of, this is U, this is dV. Well, this is going to be equal to U times V. So theta times the arctangent of theta. Come on, there we go. I really shouldn't have used the theta, but say love you. And then minus the integral of V du. Minus the integral of V theta over 1 plus theta squared d theta. But now we're doing a definite integral. So I can evaluate this at theta equals 0 and theta equals 1. I can evaluate this at theta equals 0, or the bounds on that new integral are 0 to 1. Okay. So we've got another integral that we need to do, as we always will when we use integration by parts. But how do you want to do this integral here? Well, notice that theta is 1/2 times the derivative of 1 plus theta squared, right? So this integral will just be a U substitution. If I let U be 1 plus theta squared, then du is 2 theta d theta, or in other words, theta d theta, which is what we have left here, theta d theta, is 1/2 du. So then, we'll find out what theta arctangent of theta, evaluate at 1 and 0 is in a second, minus the integral of, well, theta d theta, that was 1/2 du, and then over u, right? And I can change the bounds on this new integral. I'm not going to, so that I can keep the bounds the same for every part of this. So this is one of the times that I'm not going to change the bounds. But what is the integral of 1 over u with respect to u? Natural log of u, perfect. So this is again, well, let me write this. This is 1/2 times the natural log of u plus a constant, which is 1/2 times the natural log of 1 plus theta squared. Plug back in for u. Okay. So then we can evaluate everything. This is theta, arctangent of theta at 1 and 0 minus, well, this is 1/2 natural log of 1 plus theta squared. I switched back to theta, so the bounds are still 0 to 1. Okay. So who knows the arc tangent of 1? Perfect, pi over 4. Yes, this is 1 times the arc tangent of 1, and the arc tangent of 1 is pi over 4, right? So there's, when I plug in 1 there, minus when I plug in 0, well, that I'm going to get 0 times the arc tangent of 0 gives me 0, and then minus, well, now I'll plug in 1 and 0 into this guy. 1/2 times the natural log of 2. There's when I plug in 1, and when I plug in 0, minus 1/2 times the natural log of 1. And who knows what the natural log of 1 is? 0. Woo! So this gives us, well, I got a pi over 4 from this piece. Then this piece gives me 0. Minus 1/2 natural log of 2. Questions? Now, you might ask, say, on an exam, what if I got to here and then I plugged in the points wrong? I mean, that would be maybe 1 point out of 10. But if you got to here, if you did all the hard work to get that antiderivative and then you messed up some arithmetic, I mess up arithmetic every day. I'm not going to take off too many points. Okay, so, but did everyone follow how we got to here? Integration by parts is a very, very, very powerful technique that you need to try to master. Okay. So it also opens the door for us to do some more complicated volumes of revolution. And so find the volume of the solid generated by rotating the region bounded by the curves y equals e to the x equals 0, y equals 0, and x equals 1 about the y-axis. Okay. Now, actually, this curve or this region isn't really that complicated. But we're going to get an integral that we wouldn't have been able to do before. So let's look at this curve. Y equals e to the x. Who can draw in the air roughly what that looks like? Go down. Is it bouncy? Is it triangular? What does y equal e to the x do? Yeah, Jet has it. It grows exponentially, right? It's the exponential function. There's y equals e to the x. Just a rough sketch will do. There's y equals e to the x. X equals 0. What does that look like? Or what line is that? Yeah, that's the y-axis. Very good. X equals 0 is the y-axis. Y equals 0, same thing, is the x-axis. And x equals 1, well, that's over here somewhere. There's 1. So here's the region that we're rotating about, the y-axis. Okay. Now, before we rotate this, how does this region want to be broken up? Vertical slices or horizontal slices? I would say vertical here. If I took horizontal slices, well, the horizontal slices up here would be different than the horizontal slices down here, right? So I want to break this up into horizontal slices. So I'm going to take vertical slices. Sorry. I'm going to take a vertical slice right there. Okay. So what happens when I rotate this vertical slice then about the y-axis? What shape would I get? Cylindrical shell, exactly right. I'm going to get a cylindrical shell. Well, I haven't said what the width of this is dx. So that means the width of the shell is dx. What's the radius of this shell? Yeah, that's just x. Very good. And what's the height of the shell? E to the x. Perfect. Perfect. So then the volume of this little cylindrical shell, which I'll call dV, or d capital V. This is not anything to do with the integration by parts yet. D capital V, a little bit of volume, is, well, I'm going to get 2 pi x. That's the, if I cut it and unroll it, that's the length. The height would be e to the x, and then the thickness of the plate that I get would be dx, right? Very good. So that's the little bit of volume I get from the shell. So to find the whole volume of the shape, I'm going to take the integral from, well, what can x be between? 0 and 1. The integral from 0 to 1. I'm going to pull the 2 pi out in front because that's a constant. So 2 pi, and then x, e to the x, dx. Okay. So this is, again, a relatively simple shape. And this is why some classes just start off with teaching you techniques of integration, so that once you get to volumes of revolution, you can do really any shape. I don't like that approach. I'd rather you see something interesting and then learn techniques to help you find more interesting things. Okay. So this integral here, I need to do integration by parts. So you scream Liate to figure out what should u be and what should dv be. So what should u be? Do we have any L's in this integral? No. Do we have any I's? Do we have any A's? Yes, we do. The x is an A. It's an algebraic function. So we're going to take u to be x, and then dv, so this is u, and dv is everything else. E to the x dx. So if u is x, then what is du? dx, perfect. And if dv is e to the x dx, then what is v? E to the x, perfect. So this becomes 2 pi. So this is scratch work, scratch. This integral becomes 2 pi times, well, this is the integral from 0 to 1 of u dv. So it becomes u times v. So x, e to the x, evaluate it at 1 and 0. Minus the integral of v du. Well, that's the integral of e to the x dx. Okay. But what's the integral of e to the x with respect to x?
E to the x.
Yeah, we just did that. We just did that one up here, right? So this is 2 pi times x e to the x. And I'm going to write it all in one fell swoop. So minus e to the x, and we plug in 1 and 0. Or if you want to put that line on each part, that's also fine. It's the same thing. So let's plug in 1 and 0. Well, when I plug in 1, I'm going to get 2 pi times 1 times e to the 1 minus e to the 1. Okay. Then I'm going to subtract off when I plug in 0. Well, when I plug in 0, I'm going to get 0 times e to the 0, 0 e to the 0, minus e to the 0. Well, this is 2 pi times e to the 1 minus e to the 1, cancels. 0 times e to the 0 is 0. So minus e to the 0 is plus e to the 0. And what is e to the 0? 1, exactly right. So 2 pi times 1 is what this simplifies to. So any questions on that one? Oops, sorry. All right. Cool beans. So this brings me to something that some classes don't teach. If you bring this up to some of your friends who have taken Calc 2, they might not have seen this. But I find it to be so useful when I'm integrating something that has multiple integration by parts. Okay, so it's integration by parts. Hopefully, I've made it super clear that it's a really, really powerful technique. But hopefully, I've also made it clear that it can be annoying when you need to do it more than once, right? So there's here's an integral, the integral of x cubed times sine of x. If you were to try to integrate this by parts, it would work, but you would need to do integration by parts 3 times. Okay, but at every step of the way, your choice for u and your choice for dv would be very, very, very similar. Okay. So in situations like these where you have x to a power times maybe sine of x or maybe e to the x or maybe cosine of x, there is a very easy, it's called tabular integration way to evaluate this thing. Okay, so at every step of the way in this integral, well, the first step, I'm going to take u to be x cubed. Then my next step, well, when I take du, I'm going to get 3x squared. And so my next step, u is going to be x squared. And then my next step, u is going to be x. And so on and so on and so on. Okay, so let's look. This is for a very specific example that I'm about to show you. But suppose we want to compute the integral of f of x times, I don't have g prime of x here, I just have g of x. Okay, then if you call this g to the -1 in parentheses, if you call that the integral of g, or the antiderivative of g, and g to the -2 in parentheses, the integral or the antiderivative of that thing, then you can form the following table. Okay, at every step of the way, I'm going to choose u to be f of x or some derivative of f of x. Okay, and then at every step of the way, I'll choose dv to be the resulting antiderivative when I take antiderivatives of g. Okay, and then when you do that, you're going to draw a line from this first f down to the second row in the dv column, and then from the second row of the u column to the third row of the u column, and then you've got this dashed line here in the bottom. Okay, this seems like gibberish right now, but here's how you use this table. But how you read this table off is, if I want to do the integral of f of x times g of x dx, then this table tells me if you do repeated integration by parts, you'll find that you'll get, well, this line, the solid line means just multiply and have that sign in front of it. So you're going to get f of x times this, it's an antiderivative of g. Okay. Then I'm going to get next, I multiply this by this, and I have a minus in front of it. So minus f prime of x times another antiderivative of g. And then this dashed line just means now you take plus the integral of f double prime times that f double prime times that second antiderivative. I left out the x's, but those both depend on x. Okay. So the lines just mean multiply these things and it alternates plus minus, and you could have 20 rows in this column if you had the integral of x to the 20th times sine of x, and you would just keep doing plus minus until eventually, how do you know when you can stop? Well, once this is an integral that you can do easily. So in this last example, do I have, I think I have an example here. Yeah, let's do it with this example here. I think showing you how this is used in practice is the best way for you to see how to do this. So I want to integrate x cubed times e to the x. Now, there's no way around it. This is an integration by parts problem. But we can use tabular integration to shortcut some of the work. So again, at every step of the way, I'm going to have an algebraic function times e to the x. Okay, so at every step of the way, u is going to be something very similar, and dv is going to be something very similar, right? So at step one, well, step one is just doing this integral. So u has to be x cubed, dv has to be everything else, right? Lyautey says that I should choose u to be the algebraic function in this integral. So I'm going to choose u to be x cubed, and that means dv, I'm going to choose to be e to the x. And because the dv is at the top here, I'm going to leave off the dx. Okay. So then, looking back at this table, well, to go from this row to this row, I take a derivative to figure out that first column, and I take an antiderivative to get to the second row of the second column. Okay, so to get to the next row here, I'm going to take a derivative. What's the derivative of x cubed? 3x squared. Very good. And to go from here to my next row, I'm going to take an antiderivative. So what's an antiderivative of e to the x? E to the x. Perfect. All right. So notice, I'm going to write this out. The integral of x cubed e to the x dx. This is equal to, well, we just showed, I mean, this was really us finding u and du, and really this is dv, so this would be v. So I would take that times that, right? This is where that line comes from. So I would get x cubed times e to the x, and then minus the integral of v du. So 3x squared e to the x dx. Okay. And now we can see, oh, well, obviously this has to be u again, this has to be dv again. So now this table is really just sort of saying, okay, now I'll slide everything down. Now this is my u, and now this is dv. Well, to get du, I would differentiate. So what's the derivative of 3x squared? 6x. What's the antiderivative of e to the x? E to the x. Very good. So I'm going to connect this with a minus. I still don't know how to do the integral of 6x e to the x. We actually do. We've done that integral a couple of times, but it's not as easy as I would like. So now, how would I get one more row? What's the derivative of 6x? 6. And what's an antiderivative of e to the x? E to the x. You can see how this would be very useful when, if I have x to the 20th times e to the x, well, dv every time is going to be e to the x, right? So, and then here we go, plus, minus, plus, and then 6 times e to the x. I know how to do that, right? So let's use that table. So we have x cubed times e to the x. Let me erase this because now we can shortcut everything. X cubed times e to the x minus 3x squared e to the x. So that was that times that, plus 6x e to the x. Okay. And then, oopsies, minus 6 e to the x. The integral of that. Minus, it's a dashed line, so minus the integral of 6 e to the x dx. Yes, the dashed line means that you need to put an integral in front of the product there. Now, there are some people, the reason I didn't say this right away, there are some people who go one more step and say, well, if I take a derivative of 6, I get 0. And then the integral of 0 is just going to be a constant, right? But it doesn't always work out that way. So I didn't want to do that here. Okay. So then this is x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus, what's the integral of 6 e to the x? Yeah, 6 e to the x, right? And then don't forget the constant. And wow, that was way better than doing integration by parts, writing it out in full every single time. But it was equivalent. It was the exact same thing, right? We're just taking advantage of a couple of observations. One, if you have integration by parts where at every step u is going to be coming from the same function that you used for u as last time, then you can use that to your advantage. 2, we take advantage of the fact that the signs, I mean, just looking at uv minus the integral of v du, I mean, then we get uv minus, and then something here minus another integral, so it would be plus, minus, and then when you distribute, you're going to get plus. So taking advantage of just those alternating signs as well gives us a really easy way to compute an integral that would have been several minutes before. Now it's just make a table, multiply the right things, and you're done. So are there questions on this? Yeah.
So compared to the other examples, we obviously had balance to plug into. So
Yeah.
this integral just falls away when we're taking this indefinite.
Yeah, exactly. So if this had been the integral from 0 to 1, you do the same thing, and then at the very end, you can plug in 0 and 1 into that and take a difference. The c doesn't matter in the case of the definite integral. But yeah, you would still find the indefinite integral first and then plug in. So that's why I think this last, oh no, I didn't, but such is life.
So for each one of those products, the one without the integrals,
Yeah.
individually we'll have to do it from 0 to 1.
Yes. Yeah. If this was the integral from 0 to 1, well, essentially that's what you would do. But you could also just all at once plug in 1 into this, and then plug in 0 and take a difference. But because addition and multiplication are commutative, it's the same way if you do it in each one. So, yeah. Any other questions? Jet is a ghost right now. Ah, there you are. Okay, so let's look at one more integral. Calculate the integral of x e to the x squared. How would we do this one? Ah, I didn't trick anyone. Mark knew. Yes, this is a U substitution problem. I just showed you a giant sledgehammer in integration by parts, but sometimes you just need a screwdriver, and U substitutions are screwdrivers, right? That's a dumb analogy. But anyway, yes, this is a U substitution, because one thing that clues us into that, but isn't necessarily definitive, is that we have a composition of functions here, right? But we also used integration by parts for compositions before with sine of natural log of x. But the thing that really clues us in to the fact that this is a U substitution problem is that the derivative of x squared is 2x, okay? And so that you should look at that and say, okay, this is some function, sorry, this is some function inside of another function times almost the derivative of that inside function. This is a u substitution problem. Okay. Oops. So u is x squared. What does that make du? 2x dx, perfect. And so I can plug that in up here. Once I move we have an x dx left. So that means that, oops, 1/2 du is x dx, right? So let's plug all that in. This is 1/2 times the integral of, well, x dx is 1/2 du. So I have the 1/2 out front, and this is e to the u, right? Questions on that? So then, the integral of e to the u is what? With respect to u? Jet, what's the integral of e to the u with respect to u?
E to the U.
E to the u, perfect. And now I can add my constant. And now they ask me the question in terms of x, so I need to answer in terms of x. If it's an indefinite integral, so I get 1/2 e to the x squared plus some constant. Okay. So takeaway of this last problem is don't forget about u substitutions. Those are still very useful. U substitutions and integration by parts together are a real dynamic duo of techniques. We're going to be learning even more techniques next week of how to handle other things, because we still don't know how to handle every integral I might throw at you. Okay. If I were to ask you, what is the integral of, say, x over the square root of 1 minus x squared dx? Well, this is a u substitution problem. If I ask you, what is the integral of 1 over the square root of 1 minus x squared dx, you should hopefully recognize this as arc sine of x, right? This is just one of those integrals that we should hopefully know. But what about if we have the integral of 1 over x times the square root of 1 minus x squared dx? Well, this isn't really a u substitution problem. This 1 over x isn't the derivative of 1 minus x squared. Just x is, again, not the derivative, but it's a constant times the derivative of 1 minus x squared. So it's not quite a u substitution problem. It's not this, oops, it's not this, but we're going to see later how it's related to this and how we can sort of generalize what's happening in this integral. So that's going to be next week. We're going to be talking about trigonometric integrals and trig substitution. Okay, and that's what we do with this last integral. We use a trig substitution. Okay. Well, thank you all for paying attention. Like I said, I'm going to try and have the exams in the grade book by Friday, which means you'll be able to see what you need to correct. And if you want to get up to half of those points back, make sure to send me corrections, and you'll be able to get up to half the points that you missed back on the exam. Okay, so if you got, say, a 50 on the exam, you'd be able to bump your score up to a 75, which is great. Okay, if there's no questions, you guys can feel free to head out. If you do have questions, you can stick around and ask me, and I'll see everybody next week. Have a great weekend.
Thank
Thank
you.
you.
Thank you.